So well done, you made it to the end of the day. I'm the last thing standing between you and a good drink. So hopefully this goes nice and quickly for us all. So I'm Dan Cook, or Daniel Cook if I've been a naughty boy. So I'm a freelance big data architect, or big data technical architect. I like specifying that it's technical. A lot of words there. In reality, I sort of shorten that to I'll do anything for money within reason. But you know, I sort of work across the stack doing development as well as the solution architecture as well. So I've got specialisms in Hadoop and GIS, so geospatial information systems, so mapping in layman's terms. You wouldn't think there's much of an overlap there, but with the advent of smartphones that are out there, everyone's got geolocation data. We want to analyze that. Quite often we're in Hadoop clusters. So I've built a Hadoop as a service offering for the UK Hydrographic Office, a nice big government department in the UK. Also worked on cyber threat detection platforms with NetFlow data, looking for things like port scanning in real time, processing about 150,000 events a second. In terms of mapping, which is completely unrelated to this talk, but I'll just throw in anyway, in case anyone wants to catch up with me later, helped build the indoor equivalent to Google Maps. So for shopping malls, airports, as well as tracking people in those buildings, you know, people want to know how long people are taking through security, etc. But where did this talk all start? I just spoke about my sort of Hadoop background. And it all started here, really. This is my friends. I've got a lot of attractive friends, albeit male, not so many females. But this is what my friends get like when they talk about Bitcoin. They start off talking about technology and then they end up saying it's going to solve world peace, all of our problems, redistribution of wealth, etc., etc. And I played the ignorant card for a while. I love playing the ignorant card. It'll never work. It sounds like crap. You know, keep doing that, and eventually you've got to look into these things. I feel, you know, I get a lot of enjoyment about being ignorant, but at some point I have to challenge what I'm being told. Even my friends that didn't have a technical background were talking about smart contracts and what they could mean for their business. So my friends kept talking about this, and it was all the time. I was sat in a car on the motorway. I was at a children's birthday party. So if anyone hasn't got children and they want to know what a children's birthday party's like, it's like going to a house party, but there's no alcohol. There's normally no music, or if it is, it's not the sort of dancing music you know you want to do. There's just no fun, really. But going back to the tech, I started reading about Bitcoin, and this is one of the first things that I found. The entire world effectively is just rolling dice, trying to get those dice lower than a certain number. And what do I mean by that? So this whole concept in Bitcoin on the blockchain is that transactions arrive, you know, someone paying for their cup of coffee, or whatever they're purchasing. We group these, or miners group these transactions together, and then they hash them with a bit of random data. And the aim of the game is to get a number lower than a given number. So the network sets a number that you've got to go lower than with your hash. And what you do is you start changing this random data with your group of transactions, trying to get lower than that. The more miners that come in, the more people that are throwing those dice. So it's shorter time to get to the number, because the probability says there's more people rolling, they're going to get there quicker. So this number gets lowered by the network, always trying to keep the block mining within a 10-minute period. But crazy, right? Just the world rolling dice. That's our new innovation. And then I delved a bit deeper, but what does it mean by everyone rolling these dice? And it means this, right? I've got nothing against coal. So I'm from England, from Yorkshire in England. I grew up, my great-granddad was a miner, my granddad was a miner, my dad was a miner, and I've got baby soft hands. I'm the first one in my family to not be a miner. And one of the reasons for that is they stopped us mining in South Yorkshire. So yeah, I'm still slightly bitter about that, watching communities break up, growing up. But is this really what we want for our future? The amount of energy it takes for people to do this mining, just hashing payloads, it's ridiculous amounts. And the only places where this is really viable are the places where energy is cheap. So this is places like Mongolia, like China. And what do they burn in places like that? It's coal. It's the stuff that pollutes the atmosphere. And, you know, I read a couple of months ago now, it's a few months ago now, that the cost it takes, the amount of energy to run a house for a week to process a single Bitcoin transaction. That's someone paying for their coffee. You know, a house has been on all week using their tumble dryer, their lights, etc., heating. Is that right? But anyway, enough conjecture. We need something practical to base the talk around. I need to talk a bit about the mechanics of the blockchain. So this is a very simplified view of a transaction on the blockchain. So transactions have inputs, transactions have outputs. Inputs is your money coming in, outputs obviously going out. You can have many inputs, you can have many outputs, so you can group together money that's previously unspent. So I think the thing to mention in Bitcoin on the blockchain is all the money's within the system. So at the very beginning there was some money credited, and then that was spent somewhere. It's been spent somewhere since. Every time a block is mined, that's a new way, a new mechanism of money getting in. There's an output, a special output that occurs when a block's mined. It credits the miner with more money. So this is how the system builds up the money that's in there. And you can only spend the outputs of a previous transaction as the inputs. But what does that mean? That means that to figure out if you're actually allowed to spend those outputs, those unspent transaction outputs, UTXO, someone else must have not already spent those, or you must have not spent them earlier on. So what you have to do is you have to start at the very beginning of the blockchain. It's this append only model. And you have to scan it and say, has my output been spent here? No. Has my output been spent here? No. And keep going. You know, big O, that's a nice big ON operation. And that's quite problematic as the blockchain grows. So it's about 150 gig now for all of those transactions that have been recorded for Bitcoin since its inception. And this 150 gig, so the whole network is a bunch of decentralized nodes. So it's people like you or me spinning up a node in their basement, and to get that going, you've got to seed 150 gigs worth of data, and that takes a few days to do because other people like us that are running nodes in their basements are doing it via their normal internet connectivity. But that's not quite the key thing. I think the key thing for me that I spotted when I looked at this, which was a moment where I thought I can build a talk around this, is the inputs and the outputs are recorded as one unit here, which is great. There's no account with a balance that gets debited or credited. The record of what money's where can be determined by scanning the blockchain. So just looking at that in a little bit more detail. So input, we reference a previous output of a transaction, that UTXO reference, so earlier on in the blockchain. We'll say we're going to use that output, and then we provide a unlocking script. So the whole thing in Bitcoin on the blockchain is based around public-private keys, you know, those normal SSH things. So quite often, quite commonly, you find that someone credits some money to a public key that someone owns the private key for. If you can produce a signature with the corresponding private key, you can unlock those funds. You can then take that money and specify an amount and credit to someone else's public key, i.e. a lock-in script. But going back to that point that the inputs, the outputs, it's all recorded as one unit. So here's the hypothesis for the talk. You don't need transactions in banking. So I've worked a brief stint in the banking world, in the investment banking world, although doing software, so it's obviously not as exciting as the trader lives. And I've got a Hadoop background, no SQL background, but I've always held relational databases dear, and messaging technologies like AMQP. And when I initially saw banking, it's like, well, it's a clear use case for it. So let's say you want to move money between accounts, a message arrives on a queue, say ActiveMQ or Cupid or RabbitMQ. You take it off there, you debit one account in your relational database, and then you go to another row and you credit that row. And then you commit the transaction. So both the rows for both accounts get written and the DQ happens all atomically. And that's great. So, that concept of two-phase commits. But as soon as you say, well, actually, we don't need two accounts, we don't need to update two rows, we can just store this all as one thing, things start to change. And then looking further into Bitcoin, and this is one of those, I've gone from putting random pictures up just to random numbers now. I don't know if that's progress or going backwards. This is one of the numbers you see when you look at the scalability of Bitcoin. It's one of the numbers that gets quoted out there. This is pre-segregated witness. So the numbers actually double this now. And this is the theoretical max number of transactions a second. It's pretty small, right? But that could be said to be unfair on Bitcoin. It's quite even though it's got the publicity at this moment in time, it's still quite a niche, quite a small group of users that are actually really using it out there. Finding people who will actually take payments in Bitcoin isn't that easy. So there's never really been a need probably to push this further than what is there. It's really a virtue of the block size limit. So the blocks, there's a hard-coded value that blocks can be a particular size. In Bitcoin, I believe it's 1 meg. Obviously, recorded in transaction inputs and outputs has an average size. There's only so many transactions you can fit into a block. And given the fact that we're always trying to only mine blocks within a 10-minute window by adjusting the difficulty, you arrive at that number, given all those preconditions. Putting this in perspective with something like Visa, Visa does about 2,000 transactions per second, with a peak of about 56,000 transactions per second. So, it can't scale anywhere near what it needs to at this moment in time to meet, a worldwide demand. And you could look disingenuously when people say that Bitcoin, the blockchain, is a store of value. You could say, well, actually what they're saying there is it's going to be a niche thing used for moving high-value items. It's going to be a bit of an asset that people trade as opposed to something that's used as a currency, if you wanted to look at that unfairly. So looking at what you could do, and all of this is predicated on, let's say, our internet connection between machines is unlimited, is infinite. You're always going to hit a hard limit. So at the moment in the Bitcoin world, we've got lots of people operating Bitcoin nodes, so they could be used for mining. They're trying to actually mine these blocks, or they could be used for supporting wallets, maybe someone's own wallet or other people's wallets, and they've got to hold this entire copy of the blockchain, which, as I said, takes a few days to seed. The problem there is, let's even say you remove this whole network bandwidth problem from my machine in my basement, and a lot of it actually isn't the download speed, it's the upload speed. Most home internet providers, it's the upload that's the issue. Not only have you got to receive transactions coming in that as they're happening to be able to mine or support a wallet capability, you've also got to seed other nodes on this decentralized network, and not just one, potentially many other people to make this really work. So let's say we solved the network connection problem. We still got a problem with our disks, right? We hit our next blocking factor. which is disks can only go spinning disks at 100 megaseconds. So even with my 100 gig blockchain, let's say 100 gig for simplicity, it's still going to take 17 minutes to seed a new node arriving on the network. 100 meg, 10 seconds, a gig, times by 6 gigs, 17 minutes, just about right. Never do maths at conference. But that is going to get worse. As more transactions go onto the blockchain, more people use this, it's going to take 3 hours to seed a new node if this goes to a terabyte, which is quite conceivable in the near future. And if it's widely used, it's going to be horrific. So let's say we've got this decentralized network, but a single node isn't actually just a node, it's a cluster of machines. And that cluster of machines has something that looks like a single disk. But by leveraging a cluster of machines, you're actually going to leverage the power of all of those disks. So if you've got 10 disks in there, you're going to get it down to just under 2 minutes to seed your 100 gig blockchain, 17 minutes to do your terabyte. And not only that, you can have this system where a new cluster in the network comes along, and other clusters will seed that cluster, blocks from those individual machines. So block 1 might be owned by one machine on an existing cluster, and it'll make a network connection to one of the nodes on the new cluster. So you'll get all those 10 nodes of an existing cluster opening network connections and sending the blocks across. So this is potentially the Hadoop file system. This is how you get that unified disk. And what's also key in the Hadoop file system is you've got this append-only model. You always write at the end. But what does that mean? It means if you've got spinning disks, your platter's always there and it's always able to write. It can really max out that 100 megasecond. It hasn't got any random accesses to worry about. So that's how a new node could come along, or a new cluster, and receive the entire blockchain quickly. But that's the seed use case. What about the continual arrival of transactions? People are paying for their coffee all of the time. So you probably want to use something like Kafka. So let's say we want to go up to our 150,000 events a second, do better than Visa, which I know Kafka can, as I've done it in the past. You want a clustered message broker. So I've got a fondness of AMQP. I've used a lot of ActiveMQ, but it's always been a real pain for me whenever I've had a high throughput problem. I've always had to partition manually, create separate queues and manage things like that and put them on different machines. Kafka makes this all simple out of the box. So Kafka has this concept of a distributed commit log. Commit log in the fact it's append only. It can max out your spinning disk. There's a message coming through here. And distributed in the fact that it partitions the topic. So it takes a chunk of the queue or topic and it puts each partition on a different machine. So when someone's writing onto that, it does a random allocation and writes those messages to one node in the cluster. So your topic spans several machines and you can get that throughput you desire, just like you can when you're using HDFS as a file system. And what we probably want to do here is we want to utilize a distributed consumer system like Kafka Connect, which hangs off the back of these topics, and it actually aggregates these transactions together into blocks. We'd probably be looking for about 128 meg, 256 meg block size, as opposed to 1 meg that we've got currently in Bitcoin, just to match the size of blocks that Hadoop stores. That's sort of naturally what it sits at by default. But it's all got a bit theoretical, right? What I've just spoken about. This is what we really care about. We really care about money and knowing if I've got my money to spend. So how do you know how much unspent transaction output you've got? How much money do you have in your account? Append only is great for write. We'll be able to scale this up to hundreds of thousands of seconds, millions per second, way more if you throw the machines at it. it's not so great for the read. What happens when we get to this terabyte, 100 terabyte, petabyte blockchain? It's going to be really difficult to figure out if funds have already been spent because we've got to scan it all the way. What we need is an index pool of the unspent transaction output. So what would a talk be that mentioned Hadoop that didn't have some MapReduce? So I had to get it in there. So on the top right hand side is an even simpler view of a transaction in the blockchain. So all we've got on this is the account ID that we're using as input to the transaction, and then we've got the account ID for the output, and because there may be more than one, there's a pipe separator in there to say input account ID 1 is paying accounts 2 and 3. If you work that all the way through, you see that actually accounts 3 and 6 haven't spent money that was credited to them. So how do you do this in a Spark job, in a MapReduce job? You start off with, let's say we've got these files on disk that contain a format like that. We split down the middle. Let's just assume there's a white space character in there. We'll split on that. So instead of having a stream of transaction rows, we've now got a stream that's tuples. And on the left-hand side of the tuple, there's the inputs. On the right-hand side of the tuple, there's the outputs. And then we've got these two flat map stages. And all they're really doing is saying, look at the left-hand side of the tuple and extract out of that and create a new tuple that has the account ID and the fact that that was used as an input. And on the right-hand side of the original tuple, everything there are outputs. So take those account IDs and produce new tuples that have the account ID and the fact it was used as an output. So the new stream after this is just a set of, well, a list of tuples that on the left-hand side as an account ID, on the right-hand side just as if it was used as an input or output. So that's on map stage, and then we'll do a group. So we're going to do a shuffle, and then reduce. So at the end of this, we'll know, or we'll have account IDs, and after that, input and output, or just input. And once you've thrown away everything that's been used as an input, we've just got the outputs left. But that'll work great for our initial seed case. So we get all of the data of the blockchain, we can run a MapReduce job over it, and we can figure out what accounts have money available to be spent, where the UTXO is. That won't work for the streaming use case, the continual use case as new transactions arrive. So we need a separate system for that. And separate systems, having two ways of doing the same thing, are never great. So maybe we need to look at this in the context of, can this do everything? Can we do it differently and achieve both the seed case and the continual case, the streaming case? So all three of these are open source BigTable implementations. So BigTable, paper written by Google and implemented by Google, initially built for the nice Google search to store the inverted index. So built for a great reason, although some of these technologies aren't, particularly HBase and Accumulo, aren't as in widespread use as such a famous case as the Google search bar would imply. But they're all petabyte scale random access stores. That's what BigTable is. To the left, we've got Cassandra. So to the left is less true to the original concepts of BigTable. So Cassandra tends to go down and really appeal to those people that have worked with relational databases, like the concept of tables and an SQL base or styled query language. Whereas the right-hand side are a lot purer to what the BigTable paper specifies. So there's no SQL style query interface on HBase or Accumulo. HBase is, I suppose, the original open source implementation. Accumulo was developed by the NSA and then given to the outside world. And as a result, it's probably not quite as popular because of its heritage. But for me, Accumulo has some great features that have since been absorbed into HBase. So Accumulo had this idea of iterators, that as you retrieve values in the store, you can apply processing at the same time. HBase later absorbed that as co-processors. Accumulo had fine-grained security, which in an enterprise setting is often really important. HBase picked that one up as well. And for me, Accumulo has a cleaner API. It's really cell-driven, but yeah, I don't want to fall out with anyone. You can do what I'm about to describe with HBase or Accumulo. You quite often can use them interchangeably. So what does BigTable look like? I quite often describe it as a key value store. And then people go, Dan, it's not a key value store, it's a column family store. And you go, well, it's got a key and a value, hasn't it? So it's pretty much a key value store. The complication comes in the fact that the key is actually composed of several parts. So all of those things that are sitting under that key actually form part of it. And it looks quite confusing at first. I used HBase and Accumulo several years ago, and I thought I understood this model when I first used it. And in the past couple of years, I realised I didn't understand this model as well as I thought I did. A key point is that everything that's stored is completely ordered on the key. It's a sorted list on the key, which is across a cluster, which is pretty amazing, across several machines. So just talking about it in relational speak, your row ID you can think of as a primary key, almost. Writes on the row ID are atomic, which is good to know. So you can write several things with the same row ID, and it'll all be done in an atomic operation. And then we get into this column thing. The column qualifier really is your column in relational speak on a relational table. But the fact is that a column qualifier can actually be put in a column family. And this is really drives the storage. Things in a separate column family in the Accumulo world can be stored in different files, which is the sort of columnar-based storage and that efficient reading, which you often hear spoken about. I'll ignore the visibility for now. These stores are extremely fast at writes, and one of the reasons for that is they're append only. Again, append only. And this is what the timestamp helps you with. So if you want to update a record, you just write a later version of it, later timestamp. And then when you go and retrieve it, it just gives you back the most recent one. And there's a flexible schema here. You can, as your system's running, it's not a predefined schema. You can shoehorn whatever you want in, adds new columns, new families on the fly, which is great. So what does that mean for our transactions? How could we represent those in the blockchain world? So our row ID, so what you're looking at here is a table showing just a single transaction, a simplified view of a single transaction. And we've given that a UID in the row ID, so all the same UID, makes sense. And then we've used separate column families for the inputs and outputs. This means if we just want to read the outputs, we won't have to read any of the input data, even if we're scanning across the entire store. And then what you quite often see in BigTable stores is a concatenation of column headers. So because a transaction can have several inputs, several outputs, I've just simply prefixed the column qualifier with the index of each input and output. So there's one input in this case and two outputs, 0 and 1. And then the inputs are just saying the transaction D, the previous transaction D, where I'm going to get this money from, and then the actual output where that money was credited to. And then in the outputs, I'm doing a similar thing. I'm saying, please give this amount to this public key. You'll notice I've lost the lock-in and the lock-in scripts for simplicity. So that's great. It gives you random access to the ledger, to the blockchain. You can go looking for any transaction and find out the details of it. But it doesn't solve the unspent transaction output problem. So what we can do here is we can write an additional column family. So for that transaction I've just shown, we can actually store the facts. We can add another row in. So just looking at the bottom part of the table at the moment, the bottom row. We can add another row in. It says unspent transaction output. index 0 and a timestamp, basically saying this money is available to spend. And when someone comes along in the future and claims that money, what they do is they write the row at the top of the table and basically say, well, here's the timestamp, this is when I'm taking it, and put a delete marker in. They basically delete the thing and say, I've taken it, no one else can have it. So if someone else goes looking for that to spend it, it won't be there. And what we've done there is we've solved the UTXO problem. Well, not quite. It's now a log n, big O log n operation, because it's indexed. We can go looking for the previous transaction, the money we're spending, and we'll find it quite quickly. But is that the whole story? So I started out with this premise that you don't need transactions in banking. Does that still hold true? I sort of waffled on about the fact that it was so great that the inputs and outputs were stored together as one single unit. But that's not true anymore. What I've just done is just broken that. I've written across two transactions. So my new transaction in the future that was claiming the funds, if we just go back a second, has a different... No, it doesn't have a different one because I've not got it on there. It has a different row ID. So new transaction, I'm writing all my details that this new transaction is taking these inputs and spending these outputs. And then I'm going back to a previous transaction and saying, I took your output. So I'm writing across row IDs. And I said earlier that writing to row IDs is atomic, right? But writing across row IDs, writing to two, isn't atomic. So how do we fix this? I think first we've just got to set a precondition that we're going to reserve the money we're going to spend first. We're going to go and find all the previous transactions for money we want to spend and take that money, and then we're going to write all the details of our new transaction. And we've got two coping mechanisms here to solve our problem. The first one isn't really related to the issue I've just spoken about, but it's a necessity. We need conditional mutation. This is something that Accumulo provides. We need an atomic check and set. If we're going to check money's available to spend and then write a new record to delete it and say we've actually claimed it, we need to do that in an atomic way. Otherwise, someone else might come in and take it. So that's one of the things that's going to solve our problem. I said the ordering was important, and one of the reasons is what if my transaction has several inputs, and let's say it's got 3 inputs. I go and successfully claim 2 of those inputs, and then I can't take the third one because someone else has already spent that money. It's not available to me. I've actually just deleted unspent transaction output, the first 2 things I've claimed, and made it not available for anyone else. So I've got to release those funds, and I'll show the rows for that in a moment. This is all really about, do you want to stay in the confines of a relational database, a tried and trusted with known implementations that work for transactions, but by doing so you potentially limit yourself to the scalability of a single machine? Or do you want to unlock and scale across a cluster of machines and really go at a high throughput, but at the expense of doing that you have to compromise, and these are some of the trade-offs you have to make. You have to implement these things yourself. So writing funds, releasing funds, should I say, is quite simple. Just go back, and someone made it available. I took it, and then I need to go back and actually make it available again. Just write the row back in and say this is now available for others to spend, because I don't need it. But does that work in the case of failure? What if I've taken 2 out of my 3 inputs and then I fall over, my machine dies? I've claimed them, but there's no record that I was the one that took them before I fell over. They're just not there for someone to spend. So you don't really want to do deletes. What you want to do is actually record the fact. You want to write a new row, not tombstone row, just an update to the UTXO column of the transaction you're claiming the money from. And basically in the value, basically put your transaction ID in there and say, I took the money, it was me. And what this means is if you fall over mid-transaction and your machine starts back up, so you go back to your Kafka queue and you go, I'm going to start processing my transaction again from the beginning, because it's always nice to start again from the beginning. Your checks are slightly different then. You go, is it there to spend? No one's reserved it. Okay, I can take it. If it's not there to spend, was it me that reserved it? Is the value column, does that have my transaction ID in it? If it does, great, just carry on and go after all the other inputs that I require. So it's been a long day, and I've just delved into the world of BigTable, HDFS, Kafka, Spark. I've thrown it all in there. If you don't have a headache, I'm sure what I'm about to do will probably tip you over the edge. Distributed systems are hard. So what I've done is I've spoken about the blockchain and Bitcoin, the Bitcoin network, which is a decentralized system or distributed system. And then what I've proposed is we take each node and we make that a distributed system as well. So it's a bit like Inception. We've gone distributed system, distributed system. We're at second level of the dream or nightmare. So trying to tie it all back together. How do we do the seed case? We probably throw away what I spoke about with HDFS. One thing I didn't say is Accumulo and HBase actually do their storage in HDFS, so we're doing it anyway. But what we probably want to do is, if a new node in the cluster comes along, it's going to come along at a particular timestamp. What we want to do is we'll clone an existing Accumulo cluster in the top left. We'll say, send me all your data up to this timestamp. So find all the rows in Accumulo that have been written up to this timestamp and put them in our new cluster. But while this is happening, we want to back up all the transactions that are streaming through as people are paying for their coffee on our Kafka queue. And as soon as the seed finishes, we switch the tap and we take everything from Kafka. Politics in a presentation. So we've spoken about the fact that we're going to spin up a new Accumulo cluster. It also makes sense that we want to spin up alongside that a new Kafka cluster. Have two of them, and it makes sense from a perspective that, let's say we've got our European cluster, our Barnier cluster, as I call it. And everyone in Europe is doing their transactions and writing them onto their European topic. If transactions are occurring in the UK, oh god, this was a mistake, wasn't it? If transactions are occurring in the UK, we don't want to necessarily go off to the European cluster because of the latency issue. So we want to write them to our own cluster, to our own hosted in London, UK topic. But then we're going to get this segregation that doesn't quite work. European topic is going to have transactions on there to be processed, and the UK one is going to have ones on there to be processed. We want the entire node to function as one. And it has to for the mining of this to work without the split occurring. So the European cluster has to, or the UK cluster pulls, the Nigel Farage cluster pulls messages, transactions from the European topic onto there, which it then can send to the Accumulo cluster for processing. And similarly, it goes the other way. Free movement, fantastic. Stumble through that. But going back to this beautiful stuff, this black gold, I don't know why people are collecting bitcoins when they could just collect coal. Look at it. What about mining? So I've sort of, along the way, forgotten all about mining. This whole thing that we have to group transactions together and hash them. The way that could work in this new view of the world would be that, again, we collect them together, potentially with Kafka Connect, write them into Accumulo. Once we've got enough to form a block, we then have to do this hashing process. But as soon as a successful hash occurs, we have to actually write that back onto the Kafka topic and say, I mine this block ID, and here are all the transactions that go in it. Anyone else that is trying to mine a block with that same ID, as soon as they receive our messages and they can validate that the hash is indeed correct with our little bit of random data, they've got to abandon building the block with that ID they were trying to do and start again. So, it's just going to go through the Kafka topic twice to achieve this. But this is the real world, right? So you could easily pick holes in what I've just presented. Hopefully it's given a little bit of a flavor of Bitcoin for people that know Hadoop, or vice versa, or a little bit of both, or you just want a drink. I think that the key message for me is hopefully this has shown that you can build a banking system without transactions. I suppose people have already proved it. The Bitcoin blockchain is out there now, right? But hopefully this has made it more concrete about how you could do those debits and credits and manage what's been spent and not been spent. You could easily do this with real bank accounts. I say easily. The core of it could be done with real bank accounts. Obviously, when you come into transfers between institutions, etc., it's going to get more complex, and some of the mechanics have become really, really complicated. So I went for a really inspirational quote, and I found one that spoke about Bitcoin being the future of the monetary system and how it was going to change everything. And I thought, oh, this quote is fantastic, but I got the attribution wrong. I just realised how embarrassing that could be. I thought it was from the director of the Federal Reserve, the US Federal Reserve, but it turned out I just read the order wrong, and it was actually just some crazy blockchain Fruit Loop that was just quoting it. So I compromised and went with a simpler gold for nerds. After all, that's what it is. Questions? It's got to be one crypto question. Okay, fantastic. Everyone obviously wants a drink. Thank you very much for your time, and I hope you enjoy the evening.